I'm Daniel Reynolds, a chemical engineer.
Hi, I'm Rory Campbell. I'm a mechanical engineer.
Hi, I'm Andrew. I'm a mechanical engineer.
Hi, I'm Olivia Fadak and I am a chemical engineer.
Hi, I'm Hasek Sweeney and I'm a chemical engineer.
Hi, I'm Wyatt Madden and I am a chemical engineer. I'm with the CPM Enterprise and we are part of the DTE team.
Our team worked with DTE Energy to evaluate and improve the performance of their cooling pond used at their natural gas power plant in Greenwood, Michigan. This plant has an 800 megawatt capacity and relies on a 200-acre cooling pond to remove heat built up from the system. However, during the summer months, the plant must reduce capacity as the cooling pond cannot keep up. As you can see here, in the month of July, the plant had an output of 800 megawatts at the beginning of the month, but as the temperature of the cooling pond increased, the plant had to dial back to 70% of capacity until the temperature of the water returned back to below 95 degrees Fahrenheit. Our project focuses on analyzing this limitation and identifying possible solutions to improve heat transfer and allow the plant to run at full capacity.
In the power plant, steam is generated by boiling water using natural gas. The steam spins the turbines, which generates electricity. After passing through the turbine, the steam enters a condenser, where it must be cooled back into a liquid. This condensing step is crucial for the plant's efficiency. The cooling pond is the plant's heat sink where evaporation removes the heat from the bulk of the fluid. The plant's capacity is limited because the cooling pond is not cooling the water enough.
The main objective of our project currently is to evaluate the performance of the cooling pond and then to evaluate how we might improve the heat transfer. We specifically aimed to analyze environmental effects like wind, humidity, and temperature on the pond, estimate how much additional cooling work is needed to reach a target inlet temperature of 95 degrees Fahrenheit, and compare potential solutions such as expanding the pond, adding a cooling tower, or adding baffles.
To determine the amount of heat given off by the pond, the team used hand calculations and calculations from Perry's handbook. Once the amount of work was known, the team jumped into COMSOL multiphysics software to help better simulate the effects of heat transfer. The team started with 2D models which showed how water would flow throughout the pond, exposing areas with poor circulation. The team then created small-scale, time-dependent 3D simulations of evaporative heat transfer, but due to computational limits, larger-scale models are going to be simulated using the superior computing cluster. A 3D CAD model of the pond has been created and ready to be used in COMSOL.
The team has identified several potential solutions for cooling. From preliminary calculations, the team believes that expanding the cooling pond and installing a cooling tower are the best options. Our recommendation is to add 100 acres to the existing pond, which would allow the plant to operate at full capacity during the summer. Alternatively, a cooling tower could provide an equal amount of cooling but with a larger upfront cost. The next steps include simulating large-scale simulations in COMSOL to determine the effect on heat transfer using the supercomputing cluster. Once completed, the team will rank the solutions based on key economic factors.
In conclusion, the current cooling system limits the plant's performance, especially in warmer conditions. Our analysis shows that increasing heat transfer capacity is essential for maintaining full power output. Moving forward, our team plans to refine simulations, incorporate additional environmental factors, and further evaluate design alternatives. We would like to thank DTE Energy for sponsoring this project, as well as our advisor and supporting faculty for their guidance. Thank you.